10, good morning. This is Dr. Beck. This is another chemistry video specifically for triple scientists and at higher tier. What you're looking at the moment is the specification points for this particular lesson. We're going to just do a review of what we've been studying previously before moving on in a second video to study something slightly different. So here, if any time you want to stop the video just to note anything down, or anything you particularly find interesting, then fine, please feel free to do that and then resume the video. The second thing we're going to be looking at today and in the next video is balancing equations and then using balanced equations to work out what we call reacting masses, and then we will continue that further for slightly more complex ideas about reacting masses. So in your book, please, could you write down our title, insert the date, and then the learning objective for today. I'm going to give you a minute to do that. Just pause the video, come back to it when you're ready. Okay, welcome back. So today, quantitative chemistry, we're looking at moles and reacting masses, and it's really a review of how to use this concept of the mole to analyze chemical reactions and calculate reacting masses. First of all, I'd like to just give you a little challenge, not too difficult, hopefully. There are some hints on the screen as well. Could you answer in your book as many of these questions as you possibly can? I'm going to give you 2 minutes maximum. However, as always, it's up to you. The moment you've finished, come back to the video after you have paused. Okay, welcome back. So hopefully you'll have spotted that this is a fairly standard question. I've given you a little bit of hints, but not all the hints were useful. Not all of that bits of the help were useful. Let's just go through those answers now. So could you please get your purple pen ready for review and corrections and annotations as required. So I gave you lots of help, but some of it was not relevant. That wasn't a trick, it was just to make sure you're focused on the absolutely important parts. This represents a molecule of water. The chemical symbol for water, H2O. The relative molecular mass, interesting. What's the answer? Shout it out right now. Okay, hopefully I heard lots of people saying 18. The relative formula mass or relative molecular mass is 2 times 1, that's the atomic mass of hydrogen, and there's 2 atoms there, and 16 is the atomic mass of an atom of oxygen, and there's only 1 there, so 18. And this 18 is part of our definition of the mole. If we convert that 18 into grams, that tells us there would be 1 mole of molecules of water. So well done if you got 18. How many moles would I have if I had 90 grams of water? Shout out the answer. Great. The answer, therefore, is simply 5 moles, or 5 MOL, that's our abbreviation. We're dividing the total mass, 90, by the relative formula, or relative molecular mass, which is 18. We would have 5 moles. Excellent. Okay, so a bit of a review to begin with. In your book, please, could you write down this balanced chemical equation and then write as much as you can about what that tells us. I'm going to give you 2 minutes to do that, but as always, come back to the video whenever you're ready and pause the video now, please. Okay, you'll have written different things, I would imagine, but the fundamentals of chemistry are written in this equation, and we need to understand what's going on here. So this tells us that 2 molecules of hydrogen, the H2, react with 1 molecule of oxygen to produce 2 molecules of water. And we can tell a reaction's happening because of our convention of this arrow. It's not an equal sign, it never is, it's an arrow. Okay? This equation also tells us about the number of moles involved. Okay, So let's put that sentence we had there. 2 molecules of hydrogen react with 1 molecule of oxygen to produce 2 molecules of water. Let's think about that in terms of moles. Remember, 1 mole or a mole is just a way of counting things, atoms or molecules. And 1 mole is this huge number here, what's called the Avogadro constant, 6.02 times 10 to the power 23. An enormous number, but a very useful number. Therefore, we can turn that word molecules into moles and then use this idea of a ratio of moles. 2 moles of hydrogen would react with 1 mole of oxygen to produce 2 moles of water. Remember, we're just counting things. So 2 times 6.02 times 10 to the power 23 molecules of hydrogen would react with 1 times 6.02 times 10 to the power 23 molecules of oxygen to produce 2 times 6.02 times 10 to the power 23 molecules of water. But by using this word moles, we can use this going forward to then do other things with this equation. And this is what we're going to look at. We should remember that for any equation like this, we can calculate the masses of the reactants or the products involved. And we do that according to this equation. The mass in grams is simply the number of moles that there are in the reaction multiplied by the relative formula mass for a particular molecule, or if it's single atoms, the relative atomic mass. Okay, so we know this, we've done this before. We're just going to go through a very simple example. Let's look at the MR, the relative formula or molecular mass for hydrogen. Well, the atomic mass is 1. There are 2 atoms in each molecule. So the relative formula mass for a hydrogen molecule, therefore, is simply 2 times 1 to give us 2. The relative atomic mass of oxygen is 16. We can find this on our periodic table. The relative formula mass of a molecule of O2, oxygen, is 2 times 16, therefore 32. And the relative formula mass excuse me, for water, H2O, is 2 times 1 plus 16, as we saw in our starter task, 18 in total. Now, we've worked out the relative formula mass for each one. Now we need to convert that into a mass by looking at the number of moles of each of those things, each of those molecules. So, for hydrogen, the MR is 2. For oxygen, the MR is 32. For water, the MR is 18. We can use our equation to work out the mass. There are 2 moles of hydrogen, and each mole has a mass, each molecule has a mass of 2. There are 2 times 2 grams of hydrogen reacting with 1 times 32 grams of oxygen to produce 2 times 18 grams of water. So we've turned our equation, we've done some calculations, and we've turned that equation into the same thing but in grams. And these are the rules of chemistry. This is why chemists need to be really careful of what they use in a reaction so they can control the amount of things they are making. We can express this reaction in a slightly different way. If we have 4 grams of hydrogen, it would react with 32 grams of oxygen, and it would produce 36 grams of water. Now, hopefully you can see that mass there is being conserved. The total mass of our reactants is equal to the mass of our product, or products. Here there's only 1. Okay, but this is the idea of the conservation of mass. Now, if we had 4 grams of hydrogen and 36 grams of oxygen, well, that hydrogen could only react with 32. It can't react with all of it. Once it's reacted with those 32 grams, it's made all the water. There is no more hydrogen left, and that ratio will remain fixed, 4 to 32 to 36. We could simplify that if we want to, but we don't need to. But that's the law of conservation of mass, and this is how chemistry then works if we're going to make a particular quantity of a particular product. Let's have a look at another example. I'd like you to have a go at answering this question. I'm just going to read this out to you. What if we react 2 grams of hydrogen with oxygen? How much water will we make? Pause the video, give yourself a minute or so, and come back when you're ready. Pause now. Okay, this principle of the ratio remaining fixed. If we had 2 grams of oxygen, 2 grams of hydrogen, it would only react with 16 grams of oxygen. If we had more, it wouldn't react. It would still be there as oxygen. And it would react with the oxygen, the hydrogen would react with the oxygen to produce this much water, 18 grams, no more. That's it. Hopefully you got that. If you did, give yourself a pat on the back. Next one. How much hydrogen will we need to make 72 grams of water? Okay, give yourself 1 minute, pause the video. Okay, hopefully you didn't find that too difficult. 72 grams, we're keeping these numbers nice and simple. The principle is important. If we want to make 72 grams, everything needs to be doubled. Everything needs to be doubled. That 4 grams becomes 8 grams of hydrogen. Fantastic. So here we have 8 grams reacting with 64 grams of oxygen to produce 72 grams of H2O, of water. All right, so that was a simple review. We're now going to extend it a little bit further and do slightly more complex questions, some of them based upon exam questions. But this was our review so far of how to use this concept of the mole to analyze chemical reactions and calculate reacting masses. Using our equation, we're thinking about the relative atomic or relative formula masses, and we need to make sure that we are always keeping the same ratios of reactants and products. Here are the key points from the syllabus. Balanced symbol equations tell you the number of moles of substances involved in a chemical reaction, and you can use balanced symbol equations to calculate the masses of reactants and products in a chemical reaction. Okay, we're going to go through a couple of more complex examples, and then we're going to have a practice ourselves. In general, here is how we produce our answer. We've shown you this before. Let's just reiterate. Step 1, we construct the symbol equation. Now, in an exam, you will always be given the formulae of the reactants and products. It's really important that that symbol equation is balanced. So in between step 1 and step 2, you should always check to make sure that what you've written is now balanced. If it isn't, your answer will not be right. Step 2, work out the moles using our equation. The number of moles is the mass. Remember, the mass divided by the relative formula mass, or if it's single atoms, the relative atomic mass. It's really important you convert the mass into grams. Okay, so many students lose marks by not doing that and leaving it in kilograms or tons or milligrams. It's not possible to do this properly without converting to our base unit. In this case, the base unit is grams. Choose the correct reactant or product. If you're asked about, I don't know, iron, don't look at the equation and look at carbon dioxide, carbon monoxide. Make sure you're looking the correct reactant or product. Otherwise, you're going to get the answer wrong. Once you've worked out the number of moles, refer back to that balanced equation and manipulate that ratio between reactants, ratio between products. Is it 2 to 1? Is it 2 to 3? Is it 3 to 1? Whatever it is, that ratio must be maintained. then we can work out the mass of the thing in question by using this equation, and then convert back to the required units. So the question might say, give your answer in milligrams or give your answer in kilograms, or it may also ask you to give it to a particular number of decimal places or significant figures, or sometimes, especially for the higher paper, in standard form. Okay, so that's the routine we follow. If you want to write that down or make a note of the important parts there at any time, please stop the video and then move on when you're ready. Okay, we are going to have a go at this question. Now, this is from our booklet, so if you want to refer to the booklet actually has a mistake in it. It's corrected here. I'm going to go through this question. We have a particular puzzle to solve. 1.3 kilograms of aluminium is used for this reaction, a reaction between aluminium and chlorine. How much aluminium chloride is produced? So just think about it. You're a chemist. You want to control what you're making. You don't want to make too much, and you don't want to waste your time making too little. You want an exact amount. So you can then use this equation and figure out how much you would need of your starting materials, of your reactants. So it's really, really important we understand this principle. Okay, I'm going to flick to my camera and we're going to go through this worked example. You may need your periodic table, so if you haven't got it, go and get it, and you can follow my working on it. Come back when you're ready. Okay, here is our chemical equation. Hopefully you can see and appreciate that this is not balanced. So step one is always to have a look at balancing the equation. Now, if you're not sure how to do this, I'll refer you back to previous lessons and previous learning. I'm not going to go in detail right now, but what I'd like you to do in your book is please write this equation out and balance it. Pause the video, come back when you're ready. Okay, excellent. Hopefully you saw that it is not balanced. To balance it, I'm going to turn this odd number here. I don't like odd numbers in equations. I'm going to make it even. That makes it easier to work with. So I'm going to double everything here, Al and Cl3. Everything is doubled up. That gives me 6 chlorine atoms. So I'm going to put a 3 in front of this to make there be 6 over here. And simply then put a 2 here to give us our final balanced equation. Well done if you got that. If you didn't, again, refresh your memory of how to balance equations using previous videos. What we now do is look at the particular reactants and products we're asked about. We're asked about aluminium and how much aluminium chloride would be produced. So to be honest, we can probably forget about chlorine, but as a principle, we'll go through everything. We need now to work out the relative atomic or relative formula mass for each of these things. Okay, so aluminium, if we look it up on our periodic table, has a relative atomic mass of 27. Chlorine has a relative atomic mass, that's a relative formula mass of 35.5. Now that will be multiplied by 2 because it's a chlorine molecule. So I'm multiplying it by 2 here. Now, aluminium chloride is a little bit more tricky, so we're just going to look at the aluminium 27. Now we're going to add 3 times 35.5. Okay, perhaps I put the bracket in the wrong place, but 3 times 35.5. So let's just round up there. We've got the 27, 71, and 133.5. These are either the atomic mass or the formula masses for these things. All right, let's just flick back quickly to our question. 1.3 kilogram of aluminium is used. How much aluminium chloride is produced? Let's go back to here. Right, first of all, we need to note that 1.3 kilogram is not the correct unit. We should always convert into grams. How many grams? Shout it out. Good. So we're going to multiply this by 1000 to give us 1300 grams. We need now to work out the number of moles. The number of moles of aluminium. The equation is the mass in grams divided by the AR or the MR. In this case, it's the AR. Now we've converted to grams, so all this will work. We therefore have 1300 grams, and we're going to divide that by 27. If you have a calculator, punch that in and let's see how far we get. Okay, we have a result, and I'm going to round up, of 48.1 moles of aluminium. Okay, that's how much is contained in 1.3 kilograms in 1,300 grams. Just going to move on to another board. We look back at our equation, we remind ourselves that the ratio is for aluminium to aluminium chloride 2 to 2. So here is our balanced chemical equation. We're not interested in the chlorine, not for this, but the ratio is aluminium to aluminium chloride. The molar ratio is 2 to 2. Now we can simplify that, simply being 1 to 1. So what we're saying is if we start off with 2 moles of aluminium, we'll end up with 2 moles of aluminium chloride. If we start off with 1 mole, we'll end up with 1 mole. If we start off with 4 moles, we'll end up with 4 moles, etc. But let's remind ourselves, we started with 48.1 moles of aluminium. Therefore, we must end up with 48.1 moles of aluminium chloride. That's the way chemistry works. This is why the mole is so useful. We will end up producing 48.1 moles of aluminium chloride. The question was how much mass will be produced? Well, the mass in grams is the number of moles times by the relative molecular mass. We know the number of moles, 48.1. We calculated the relative molecular mass already. That was 133.5. And therefore the mass in grams will be 6427.7 recurring. Okay, not the most elegant number, but it's the right answer. Now we could convert it to kilograms, and hopefully you know how to do that. However, it doesn't ask us to. This will be ultimately the correct answer. 6427.7 recurring grams, 6.4 kilograms. Okay, excellent. Next, let's have a look at the second question here. And I'm going to just do a model of how we do this. Very, very similar. Okay, so it's not going to be hopefully too taxing. Do it a little bit quicker, perhaps this time, so we can then move on to that. So let's go back to our equation. Here it is. Oops, it's balanced. This is what we wrote earlier. Okay, we are being asked to work out how much chlorine is required to react with 77 grams of aluminium. Right, okay. This is a little bit more tricky. So we're going to look at aluminium and 77 grams of aluminium. Just focus this. So 77 grams of aluminium. First of all, we need to recognize that, first of all, it's the correct unit of grams. So this then can allow us to work out the number of moles. Now each mole is 27 grams, so we have 77 divided by 27, and we can get our calculator and work this out. (77) divided by 2.7, 28.52 moles. Okay. Of aluminium. 20. No, I've got that one. I made a mistake. 2.852. Just going to double check that. 77 divided by 27. Yeah, my mistake. 2.85 moles of aluminium. Fantastic. Back to the plot. Let's have a look again at our balanced chemical equation. This time we need to be aware that the molar ratio is not simply 1 to 1 or 2 to 2, which you can simplify to 1 to 1. The molar ratio is 2 to 3. 2 to 3 of aluminium to chlorine. Okay, so we have 2.85 moles of aluminium. Let's make that a bit clearer. We need to scale that up. What I'd like you to do is think about that for a second and then have a go at working out how many moles of chlorine we will need to react in the correct ratio with aluminium. Give yourself a minute, pause the video, come back when you're ready. Okay, hopefully you recognize that we're going to need to multiply this by 3 over 2. So we multiply by 3 and divide it by 2. That will give us the correct ratio of 4.28 moles of chlorine. 4.28 moles of chlorine. Excellent. So 4.28 moles of chlorine. We can then work out the mass of chlorine that's going to be produced. And remember, it's always in grams. It's the number of moles, I'm going to simply call that N, times by the MR. The MR, not the AR. It's a molecule of chlorine. Therefore, 4.28 times 71, and this will give us the answer in grams. So here we go. Notice on my calculator, I haven't rounded anything up on the screen. Please don't until the final answer, otherwise you may be out and you may not get the accurate answer. Here at the end, we can round up when we've done the whole calculation. 303.7 grams. So the question was, how much chlorine will we need to react with 77 grams of aluminium? We would need 303.7 grams of chlorine. Okay, so today's video has been a review of how to use this mole. I'm going to now show you, I'll let you have a look at a past paper question, a genuine past paper question, so you can see exactly the kind of thing to expect. About using balanced symbol equations to calculate masses of reactants and products. So here we go with a past paper question. Carbon monoxide reacts with, don't worry about the word reduces for now, it's something we'll look at in a future topic, but simply is going to react with iron oxide, iron 3 oxide. Here is our equation. Notice it actually has been balanced. You're given the relative atomic masses of the relevant things. So have a go at this question. It's worth 3 marks, so I would suggest no more than 5 minutes. You'll need a calculator. When you're ready, away you go. Okay, welcome back. Hopefully you didn't find that too taxing. We're just going to go through the answer with me, and then I'll show you the actual mark scheme. All right. So back to our camera. We have the chemical equation. It was already balanced for you. Let's just go through that now fairly rapidly, but hopefully by now you understand what we're doing. This is iron 3 oxide, Fe2O3. I'm going to react it with carbon monoxide, and it's going to produce iron, and it's going to also produce carbon dioxide. Now, notice you weren't given the relative atomic mass of carbon because we don't need to worry about either carbon monoxide or carbon dioxide. We're just going to focus on these two chemicals here. Okay, first of all, we need to calculate the relative formula mass of iron oxide. If we do that maths, we end up with 160. And the relative atomic mass of iron is 56. Okay, so we were told we had 30 tons. 30 tons. Well, 1 ton is 1,000 kilograms, and 1 kilogram is 1,000 grams. So we need to convert this to our base unit. So this will be 300 times 10 to the power 6 grams. We're going to, however, divide that by 160. And that will give us the number of moles, which is 1.875 times 10 to the power 6 moles of iron oxide. The molar ratio, if we look at the equation, is 1 to 2. 1 mole of iron oxide to 2 moles of iron. We're going to need to convert this. We're going to actually need to multiply this number by 2 to make that molar ratio work. So 1.875 times 10 to the power 6. We're going to multiply that by 2. That will be 3.75 times 10 to the power 6 moles of iron. Moles of iron. Each iron has an atomic mass of 56. So the AR is 56. We are simply going to multiply 3.75 times 10 to the power 6 times by 56. That will give us 210 times 10 to the power 6 grams, and a final answer of 210 tons. Okay, wonderful. If you got that answer, give yourself a pat on the back. You're working at that really high level and fully ready for our next lesson. I'm just going to show you the mark scheme. It's a little bit complicated. They've used a slightly different version, or as a second objective, they've done something very similar to what we have done. Okay, so have a look through that mark scheme. The correct answer ultimately is 210 tons. Now notice, if you don't show any marking, you will still get the right, you'll still get 3 marks if you get the right answer. This is not a thing you can do in your head easily, and I would really recommend you show your working. Even if you make a mistake somewhere in there, you might still end up with 1 or 2 marks out of 3. So please do not try to do this all in one go just by punching numbers into a calculator. Chances are you won't get it right, and you'll miss out if you do not show your working. Okay, so this lesson then has been looking at moles and reacting masses. It's been mostly a review, but hopefully if we got all the way to the end and we got everything right, we're in a good position to move forward with our next video. Thank you very much. I will see you next time.